Hello students, today let us see the line spectrum in hydrogen atom. Line spectrum is emission spectrum. The electron present in the hydrogen atom is present in the first orbit. First orbit means n is equal to 1. On the absorption of energy, this electron is excited to either second, third, fourth, fifth or sixth orbits depending upon the amount of energy available. Depending upon the amount of energy the electron absorbs, it is excited to any of these higher energy level. The electron in the higher energy level is unstable and it comes back to the lower orbits by the emission of the energy absorbed during the excitation, right? So, during this de-excitation, this is called the de-excitation, when the electron returns back to the lower energy level, it may come directly to the first principal quantum number from second, third, fourth, fifth or sixth directly. When the electron comes back directly to first orbit, the lines observed are known as Lyman series of lines. Lyman series. And when the electron comes back to the second principal quantum number, the lines observed are known as Balmer series. The electron may come from any of the higher energy level to the first principal quantum number in case of Lyman series, and any of the higher energy level to the second principal quantum number in case of Balmer series. If the excited electron comes to the third principal quantum number, it is known as Paschen series. Paschen. If the electron comes to number 4 principal quantum number, fourth principal quantum number from fifth or sixth, it is known as Brackett series. If the electron comes from 6th to 5th principal quantum number, it is called Pfund series. P-Pfund or Pfund series. If the electron comes back from higher energy level to the 6th principal quantum number, it is called Humphrey series. Humphrey series of lines. So, there are 6 series of lines observed in the hydrogen spectrum depending on the lower orbit to which the electron is de-excited, right? During this de-excitation, the electron may come directly or in steps, right students? So, we have to calculate the difference of energy between the two orbits. That much amount of energy is released, that as a photon. This photon is observed as a line in the line spectrum of hydrogen atom, in the emission spectrum of hydrogen atom. Okay. Now, what is the difference of energy between the two energy levels? Difference of energy is E2 minus E1, where E2 is the energy of higher orbit and E1 is the energy of lower orbit. P2 is the energy of the orbit from which the electron is coming, and E1 is the energy of the orbit to which the electron is coming, right? Now, what is the energy of a particular orbit? The energy of an orbit is En. E is the energy, N is the energy in that particular principal quantum number, right? It is minus RH 1 by N1 square. Minus. Why the energy is negative? The energy of electron in a particular orbit is always negative. Why it is negative? Because the electron is continuously moving. It is the nucleus. Around the nucleus, the electron is continuously moving. The energy of moving electron is always less than the energy of electron at rest. Energy of moving electron. Moving electron is always less than energy of electron at rest. energy of electron at rest. Therefore, as the electron is continuously moving around the nucleus, the energy of electron is always negative, right? Now, what is the difference of energy? The difference of energy can be calculated by using this. Minus RH N2 square. N2 is the higher principal quantum number from which the electron is coming, minus RH by N1 square. N1 is the lower principal quantum number to which the electron is coming back, right? On solving we get RH into 1 by N1 square. This minus of minus becomes plus and RH is taken as common. 1 by N1 square minus 1 by N2 square. What is this RH? RH is the energy of electron in an orbit. Energy of electron in an orbit in joules per atom, in the units joules per atom, right? The value of this RH is 2.18 into 10 power minus 18 into 1 by N1 square minus 1 by N2 square, right? Now, if we consider an electron is coming from N is equal to 4 to N is equal to 2. From fourth principal quantum number to second principal quantum number, the electron is coming. Now, how this equation changes? It is delta E is equal to 2.18 into 10 power minus 18 into 1 by the lower principal quantum number 2 square minus the higher principal quantum number 1 by 4 square. On solving this, we will get the difference of energy between the two energy levels. This much amount of energy is emitted as a photon, which is observed as a line in the emission spectrum of hydrogen atom. Right, students? We will discuss some of the problems now. Students, now let us get the equations for the frequency and wavelength of the emitted photon during the de-excitation of the electrons from higher energy level to the lower energy level, right? Now we know that delta E is equal to h nu. H nu is the photon emitted during the de-excitation. We know the formula for delta E. Delta E is equal to RH 1 by N1 square minus 1 by N2 square. Okay, so if we take H, this Planck's constant to the right side, then nu is equal to RH by Planck's constant H 1 by N1 square minus 1 by N2 square, right? What is the value of Planck's constant? It is H is equal to 6.625 into 10 power minus 34 joules in joules unit. So if we substitute this value here, what is RH value? RH value is 2.18 into 10 power minus 18 divided by 6.625 into 10 power minus 34 1 by N1 square minus 1 by N2 square, right? Now on simplification we get 3.29 into 10 power 15 into 1 by N1 square minus 1 by N2 square. N2 square, right? This is in hertz because the unit of frequency is hertz. So this is the frequency in hertz, the frequency of emitted photon in hertz. How to get the wavelength? Wavelength is equal to, we know E is equal to hc nu bar. hc nu bar. So, and nu bar is equal to 1 by lambda. So, hc by lambda. E is equal to hc by lambda. So we will get 1 by lambda, which is equal to nu bar, is equal to RH by HC. RH by HC into 1 by N1 square minus 1 by N2 square. Right, students? So this is a simple relation. We know that E is equal to HC by lambda, or HC nu bar, and nu bar is the wave number, is equal to 1 by lambda. So by using this equation, we can get either wave number or the wavelength of the emitted photon during the de-excitation. During the de-excitation, that is when the electron comes back to the lower energy level from higher energy level. The wavelength is in centimeter inverse. The wave number is in centimeter inverse and wavelength is in centimeters. On substituting these values, h is Planck's constant and c is the velocity of light. On substituting these values, we will get 1 by lambda is equal to 1 by lambda, or nu bar is equal to 109,678. 109,678 into 1 by N1 square, as it is 1 by N2 square. Right? This value is known as Rydberg constant. Rydberg constant. And this equation is known as Rydberg equation. This equation is known as Rydberg equation. By using these equations, we can calculate the difference of energy or the frequency or the wavelength associated with the emitted photon in the emission spectrum.